All right, today we're putting on our detective hats and heading into the chemistry lab. Our mission? To crack the case of the unknown salt. And we're going to do that by systematically identifying what's called its acid radical, or as most chemists just call it, its anion. So picture this, you're in the lab and you're handed a vial of some mystery white powder. What do? Do you just start mixing things randomly and hope for the best? Absolutely not. In qualitative analysis, every single test is a deliberate step. It's a question you're asking the substance, and the reaction you see? Well, that's its answer. And it's another clue that gets you one step closer to solving the mystery. You know, every good investigation needs a solid game plan, and here's ours. First, we're going to classify our potential culprits, the anions. Then, we'll start interrogating them with a series of tests, starting gently and then escalating if we need to. And finally, once we think we've got our prime suspect, we'll run one last test for that undeniable proof. Let's get to it! Okay, first things first. We have to narrow down the field of possibilities. I mean, a detective wouldn't treat every suspect the same, right? And neither do we. We group these anions based on how they react, specifically with different kinds of acids. This first step of classifying our suspects is absolutely crucial for a successful investigation. Think of this table as our investigation playbook. And notice the logic here. It's all about escalation. We start with a weak, dilute acid. If we get a reaction, boom, we know our suspect is in group 1. Easy. If we get nothing, we escalate to a strong, concentrated acid for group 2. Still no reaction? Well, that tells us our suspect is one of the really tough ones in group 3, and they need their own special kind of test. This strategic approach is everything. All right, let's start our interrogation with our first technique, dilute sulfuric acid. Now, this isn't some brute force method. It's a very specific question aimed at one particular suspect that we know is going to talk under this kind of gentle pressure, the carbonate ion. The test itself is pretty straightforward. You take a little bit of your salt, add a splash of dilute acid, and then you just watch. What are we looking for? Bubbles, effervescence. But hold on. Lots of things can bubble, right? A good detective doesn't just see a clue, they verify it. We have to prove that the gas being made is exactly what we think it is. This fizzing, this brisk effervescence is our smoking gun for a carbonate. And why is that? Because when you mix an acid with a carbonate, it kicks out carbon dioxide gas. But, as we know, you can't convict someone on just one piece of evidence. We need to catch that gas and confirm its identity. And here it is, the moment of truth. We take that gas and bubble it through lime water, which is just a solution of calcium hydroxide. If the gas really is carbon dioxide, it's going to react and form calcium carbonate. That's basically chalk. It doesn't dissolve in water, so it makes the solution look milky. That is our definitive proof. If the lime water stays clear, well, our suspect isn't a carbonate, and we move on to group 2. So, what if there was no reaction with the dilute acid? That's a clue in itself. It tells us our suspect is a bit tougher than we thought. So, it's time to escalate. We're going to bring out the big guns. Concentrated sulfuric acid. This stuff is a way more powerful reagent, and it's designed to force a reaction out of our group 2 anions. Okay, this is where having a keen eye and a good nose really comes in handy. Each anion in this group gives off a totally unique signal. For the halides, chloride, bromide, and iodide, the color of the fumes is a dead giveaway. And for acetate, that sharp smell of vinegar, it's absolutely unmistakable. These aren't just clues, they're like the distinct signatures of our suspects. But what happens if even the super strong concentrated acid doesn't get a reaction? Well, remember, a lack of reaction is also a clue. It tells us our suspect belongs to group 3. These anions, like sulfate and phosphate, are pretty stable, and they just won't react with other acids. They need their own highly specific tests. So to nail these guys down, we need specific reagents. For sulfate, we use barium chloride. It forms this thick white precipitate of barium sulfate, which is famously insoluble. It won't even dissolve in strong acids. And for phosphate, the test is even more dramatic. You add ammonium molybdate, warm it up a little, and you get this bright, canary yellow precipitate. There's no mistaking that for anything else. So at this point, we probably have a prime suspect. Our preliminary tests have pointed us in a very specific direction. But are we ready to close the case? Not quite. In science, just like in detective work, we need to be absolutely 100% sure. So it's time for the final proof, the confirmationary tests. And this is just so important. We need a test that is so specific to our suspect that it leaves zero room for doubt. This is basically the chemical equivalent of getting a perfect fingerprint match at a crime scene.
Okay, so let's say all our initial tests are screaming chloride. The chromal chloride test is the definitive way to prove it. This one is a classic for a reason. It's incredibly specific and gives a really clear visual result that is almost impossible to misinterpret.
Now the procedure here has to be done carefully. You mix the salt with potassium dichromate and acid to make these reddish-brown vapors. But here's the catch. Other ions might also make reddish-brown vapors. The real confirmation is step 2. You bubble those vapors through sodium hydroxide. Only chromal chloride will make that solution turn yellow. And that, my friends, is our undeniable proof. Case closed.
Now, this is a brilliant example of using a second chemical to tell similar-looking suspects apart. Silver nitrate will make all the halides form a precipitate, a solid. But the real key isn't the color, it's how they react to ammonia. The silver chloride dissolves completely. The silver bromide barely dissolves. And the silver iodide, it won't dissolve at all. This difference in solubility is the critical piece of evidence we need to tell them apart for sure. And now, for one of the most famous tests in all of chemistry. If we think we have a nitrate ion on our hands, the brown ring test is the classic, most elegant way to confirm it. Honestly, doing this test is almost like an art form. You mix your salt solution with some freshly made ferrous sulfate. Then, you tilt the test tube and you carefully gently let concentrated sulfuric acid trickle down the inside. The key here is you do not shake it. The dense acid will form a layer at the bottom. And if nitrate is present, you'll see this beautiful, sharp brown ring form right where the two liquids meet. That ring is the unmistakable signature of the nitrate ion.
So, when you boil it all down, the real takeaway here is that this kind of analysis isn't about memorizing a bunch of random reactions. It's a process of pure logical deduction. You start broad, you use preliminary tests to narrow down the possibilities, and then you use a super-specific confirmatory test to prove your case beyond a shadow of a doubt. It's chemical detective work at its finest.
In the end, what we're really doing here is learning to listen to the language of chemistry. Every color change, every bubble, every smell, it's all a piece of information, part of that salt story. So the next time you're in the lab with an unknown substance, remember, you're not just a student, you're a detective. Listen closely, and the chemicals will tell you their secrets.